Okay. As you may have seen, the next project is out on naive Bayes. Today we will transition from naive Bayes to logistic regression and to empirical risk minimization, and then the next project actually will be shipped out. So there will be one more project before the midterm. So please there will be overlapping. So please get started with the naive Bayes that you're on track. All right. So we've been talking about naive Bayes, and the general idea is you fit this distribution. You want to know P of y given x, and you say, well, that's proportional to P of x given y times P of y. Do people know what that proportional means? Raise your hand if that makes sense. Okay, so it's basically up to normalization, essentially, right? So that you divide it by something, then you have equality. Divided by something doesn't matter in this case, because we're just interested in the ratio of two classes. All right, and so, well, let's say we have two different classes, +1 and -1, and we basically estimate these two distributions individually. So what we do is we just estimate how often do we see that class +1, how often do we see the class -1. And here we actually have the probability of x given y, and here this is where we make the naive Bayes assumption. And we went over several cases last time, including multinomial and Gaussian. Right? Basically, in the Gaussian, we take each feature and fit a Gaussian. And in multinomial, we assume that each feature is a count, how many times we've observed that feature. So let us look at the multinomial setting for a second. So assume we have a classifier, and we say that what it does, it predicts a +1. Okay, so when does it predict a +1? Well, if and only if P of y given x, y equals +1, is greater than P of y equals -1 given x. Okay, so in this case, you basically evaluate both of these. And you say, what's the probability that my data point x has, this here is a +1. Y equals +1, has a probability +1. What's the probability that it's has a label +1. What's the probability that it has a label -1? If this one is larger, then the Bayes optimal classifier would say, go with the more likely one. So, well, this decomposes, so we can actually plug in these following terms. So we basically say, well, that's the case only if, so P of y for +1, let me just do a +1 here, +1 is greater than the same term given -1. Okay, so that's the same thing, right? So I'm basically saying, I'm just taking, exactly, this is just Bayes rule, right? And I say this one, the probability that basically we get a label +1 must be larger than we get a probability -1. Raise your hand if you're with me. All right, awesome, good stuff. Assume we do a multinomial distribution. So if you remember from last class, multinomial distribution, doesn't affect this thing here, but affects the assumption, that we are making about the distribution of the features. And let me just say these are vectors. So we saw from last class, this is the distribution here is basically, we had this m factorial over x1 factorial xd factorial times the product alpha equals 1 to d theta alpha c x alpha. So what this is basically, we go through all our features from 1 to d, and we say, what's the probability that we rolled exactly that feature x alpha times, where x alpha is basically the value of that particular feature. Okay, so that's in the spam setting or something, we have an email, we go through every single word in the dictionary, and we say, what's the probability that we observed exactly that word that many times, right? Given that it's a particular class, so here the class is +1. Okay, raise your hand if you're still with me. Okay, good. So then I do the same thing for the other one. Oh, sorry, times P of +1. So the same thing for the other, for the case where I have xd factorial. And now I say the product, I go over all my features. And now I roll the different die. I roll the -1 die. So that's now the spam or not. This is the spam. This is the not spam die. And I say times the probability of -1. Okay, so all I did here is I plugged in this, the definition, from the multinomial distribution, in for p of x given the label. Yes?
Can you write larger? It's hard to see in the back.
Oh, yes, I can write larger. That's right. Okay, good. I guess you can't read these. Doesn't matter, because they're actually the same on both sides. So we remove these constants. And so now we're left with this expression, right? We basically have a product of many of these probabilities on the left and on the right side. And so what do we do when we have a product of many probabilities? Who knows it? Because we're computer scientists? Good. We take a log, right? So that's exactly what we do. No? Damn it. All right. So now we can take the log on both sides. Doesn't change anything, right? It's a monotonically increasing function. So if the log of the left side, if the left side is larger than the right side, then the log of the left side must be larger than the log of the right side. We can take the log because both must be non-negative. Well, it must be positive. Right? So let's take the log. So then we get log of p of +1 times the sum over alpha equals 1 to d log of, this is x alpha times log of theta alpha of +1. This is not alpha plus, this is label +1, right? Y equals +1. Must be greater than log of p of -1 times the sum over alpha equals 1 to d, and now x alpha times log of theta alpha, and label is -1. One more time, what I did is I just took the log on both of these sides. Okay? Any questions? Did I forget some term? There's a plus, sorry. Was that your concern? Okay, good. Raise your hand if you're still with me. All right, good, you're holding on. Good, good, good. All right, so, well, here's what we can do, right? We can now actually collect the terms with respect to x alpha. Like we always basically, what is this, right? It's a sum of many terms, right? We have x alpha times some term, right? We have the same thing on this side. So what can we do? We can pull these sides over here. Okay? So if that happens, well, we get the following. We say we get log of p of +1 minus log of p of -1. Here what I did, I took this term and just moved it over. All right? And then I said alpha equals 1 to d. And then I take these two sums and I move the right sum on the right over to the left. All right? So what do I get? X alpha times log of theta alpha +1 minus log of theta alpha -1. And that must be greater than 0. Okay, one more time. So what I did, I just collected terms, right? I just subtracted the right side from the left side. And so I put the two log probabilities together and I put these two summations together. Raise your hand if you're still with me. All right, good. You're almost there. You're almost there. So here's what we do. We call this here W alpha. Okay? And we call this here B. Okay? So this here is one constant. This is just a scalar. And this here is for every alpha is one value, right? So we actually get alpha goes from 1 to d. There's a d-dimensional vector. So what does that mean? Ta-da! W transpose x b plus b is greater than 0. What have we just shown? Can anyone tell me?
Linear classifier.
It's a linear classifier, exactly, right? It's nothing else than a linear classifier. But we just have a very specific way of finding the W's, right? So the perceptron was one way of finding the W's. You have the perceptron update rule. A naive Bayes is another way of finding the the weights of W. And you just define them this way, where you estimate the thetas using MLE, and then you compute your W's and your B that way. Question?
So this works for multinomial features, but does it work for categorical features too?
So it doesn't work for all distributions. It depends on, yeah, that's right. And so actually, this will be the homework. The homework we will actually look at other distributions. That's, yeah, good question. So you can easily make distributions that doesn't work at all anymore. But actually, the interesting thing is you typically, the most common case is actually multinomial, because it works really well for these kind of text document classifiers. Right? Actually, it's also true for Gaussian naive Bayes. Yeah. Yeah?
So what if your data set isn't linearly separable?
Ah, that's right. Good question. Right. So perceptron. Does anyone remember what happens if you run the perceptron algorithm on a data set that's not linearly separable? You're screwed. Good. You're screwed. I like it. Right. It just loops forever. Right. Like it never ever converges. So what does naive Bayes do? Can anyone tell me? Does it loop forever? The answer is no, because there's no loop. Yeah?
It gets an answer that's like reasonably good, but not perfect.
It gets an answer that's reasonably good. And what does it do, essentially? It just fits the two data sets, right? The two classes with the multinomial distribution, and then says, if that was true, if the data really came from these multinomial distributions, then here would be the hyperplane, right? It doesn't, right? But, but if it was true, if the data actually was the way I modeled it, then actually I would have a really good hyperplane, right? That's basically what it is. And even actually if your modeling is correct, it doesn't need to be linearly separable, right? You could have two Gaussians. Let me show you an example here. You could have two Gaussians, right? They're basically like, I have my Gaussian here, from which I draw my axis. And then I have my second Gaussian here, where I draw my circles. And these are certainly overlapping, right? That's okay. Right, the naive Bayes classifier would model both of these as a Gaussian if you use the Gaussian naive Bayes, and would then basically find a hyperplane that best separates these two Gaussians. So it would basically find a hyperplane here. But that's a very important distinction to make. It does not find a hyperplane that best separates the positive from the negative points. It finds the hyperplane that best separates one distribution from the other. And it fits these distributions from the data. Right? So that's an important distinction to make. Any questions? Yeah?
Does this mean that naive Bayes is generally superior to the perceptron?
So there's a few advantages of naive Bayes. So one thing is this here does not require any loops over the data or anything, right? So this is really, really fast to estimate, and it's very fast to update. So that's very advantageous. The second thing is you don't have this danger. If you would have a spam filter that's a perceptron, that would be really terrible, right? Because occasionally you're going to misclassify a spam email as not spam or something. Now your data set is no longer linearly separable, right? And basically now will loop forever, right? So in that sense, that's true, right? The perceptron is not generally used anymore, but derivatives of it are used. And actually, that's exactly where we are going now. The perceptron is a discriminative algorithm. So what the perceptron is trying to do is try to model y given x. And naive Bayes is a generative algorithm that models x given y. But there is a formulation of this that actually flips it around. And I will get to this after this question. Yeah?
So because this is a generative model and we're modeling the two distributions, like not only does it create a hyperplane that is a linear classifier, in principle you should be able to pull out posterior probabilities for every data point of its membership of
right, that's a very good point.
Membership.
That's a very
We haven't gone over any of that yet. Like,
no. So he says one advantage of the naive Bayes algorithm is that at the end actually you get a probability, right? So you can actually say, at the end I get P of y given x, right? I get the probability that it's spam and the probability that it's not spam, right? Sometimes that doesn't matter. I just want to know, should I move it in the inbox or not? But sometimes that's really crucial, right? So for example, if you're a doctor and you say, let's say, I want to do some brain surgery, and you want to say, is this brain surgery necessary, right? Yes or no, right? Well, you may be interested if the probability is just 51% versus 49, right? You may want to do another CAT scan, or I don't know, who knows what, right? So these probabilities, basically these probabilities give you a measure of certainty, and that comes for free in naive Bayes. Actually, it's not that that you have to have a generative model to do this. So discriminative model also have these probabilities, can have these probabilities. And actually the one we will talk about in a minute also has these actually. But the perceptron does not. Someone just had a question? Oh yeah.
Could you just repeat what you said about how this doesn't find the hyperplane that separates the two point distributions?
Yeah, so what naive Bayes does, right? It takes your data, and you have points here, and you have points here, right? And then it models these data points with a distribution. That's the step when you estimate the theta for your P of x given y. So you make a decision here. You say what's your distribution P of x given y. You say that's multinomial, right? You do this as a data scientist who understands the data, right? So that's where your knowledge comes in. Once you've made that decision, now your distribution has some parameters. For example, in the multinomial is this particular theta, and you fit that theta. That's the maximum likelihood. Okay, the first step is you decide which distribution you use. Second one is you estimate the parameters. At this point, now you substitute the data with the distribution. So you're now saying, if my model is correct, this was drawn from the following distribution. Here, these are kind of these surface plots. Kind of think of this as a mountain that comes out of the blackboard. And then at this point, you don't look at the data ever again. Right? You're now separating just these two distributions. This can go horribly wrong, and we saw these examples last time when I asked you guys what data set would break it, right? If you, for example, have something that you have some points here really close by and a lot of points far away, right? In this case, and if you say it's a Gaussian distribution, well, what it's going to do, it's going to, basically just, have a Gaussian distribution here, maybe a little bit of something like this, right? And so what would it do if we have these points and this distribution, it would find a hyperplane somewhere in the middle and basically sacrifice these points. Right? The perceptron would never do this because it separates the data. Right? Naive Bayes first approximates the data, models the data, and then basically using that model gives you the best decision boundary. But if the model is wrong, it gives you a wrong result. Does that make the distinction clear?
Yeah, so the perceptron would, like you said, would never sacrifice those 2 points.
That's right. It would keep updating until it finds a decision boundary that captures these, right? On the other hand, if there isn't such a decision boundary, it would just keep going forever, right? Whereas naive Bayes is like, whatever, Yeah.
So say the naive Bayes gives you a prediction of like 99% for class. Could you incorporate that test point back into your data and retrain to it?
You guys are clever. So his question is the following. Let's say I take my data set and I make a prediction, and I have a test data point. And I'm pretty sure, right, the naive Bayes classifier says this is, 99.9% confident. This is spam email. The fact that I'm so sure, right, means that it's probably right. So kind of just take this data point now, put it in my training data. Now I have more training data, and now I retrain. Right? It's called what is it called? Self-training, and it can work. The problem is typically that if you add the ones that you're really confident about, you're actually not gaining much because you already knew about this point anyway. So what you really would like to add is the ones that you're kind of right, but they're right on the edge, right? Of course, that's a risky business. People have gotten it to work, though. You can basically do this, but there's a little bit more to it. But yes, in principle, it's a good idea. Okay, any more questions? Yeah. Sorry, do you? If you don't have a closed form here?
Yeah, the X and the Y.
Oh, I see. If this, well, Yeah. I mean, if you don't have that, then it gets nasty, right?
But for the exception, you don't need one. You don't need
You make no modeling assumption. You don't need a distribution. So that's certainly the advantage of the perceptron. That's right? So the naive Bayes, like the naive Bayes basically, has an advantage when you have a good estimate of what that distribution is, right? And ideally, if the naive Bayes assumption holds, right? That's where it really kicks in. Okay, so one thing that will be on the homework assignment, the next, I think it's coming out this week actually. You have to derive the following thing, that if you actually use a Gaussian, like if we just did this for multinomial, if you do the same exercise, right? We started out with saying, what's P of x y given x? And then we went through it and we plugged in the naive Bayes formula and plugged in the formula for multinomial distribution and so on. And at the end, we basically came up with a linear classifier. If you do the same thing for a Gaussian naive Bayes, then you get the following expression. That's 1 over 1 plus e to the minus w transpose x times y, where y is element of plus 1 minus 1. Okay, so at this point you just got to believe me, and then if you don't believe me, well, great, you can actually verify it. So maybe I give you a minute to digest this equation. I want you to become one with this equation. So discuss it with your neighbor and think about the following. Let's call this thing here z, right? So this w transpose x. So z times y. Think about the following. What does this function look like if z times y becomes really large? It becomes really low, like negative, right? Really, really negative. And what does that tell us about this function? So think about this, discuss it with your neighbor, and just get some intuition. I'm going to draw it in a minute. So try to draw it, right? It's a function of, this here is z times y. Okay, who can tell me what this function looks like? Who is brave enough to even can to just describe it? Yeah?
When z equals 0, is minus infinity, it reaches 0. And when it is plus infinity, it reaches 1.
That's right? So, let's say here's 1, here's 0.5. So at plus infinity, it's 1. At minus infinity, it's 0. Right? So why is this? If this becomes really, really large, right? Then we have 1 over something really, really large becomes 0. So we actually have to, so if this here is negative, you multiply with a negative. So this becomes really, really large. So it's inverse, right? So at this point here where c times y is really, really, really negative, you're multiplying that with a -1. So this here becomes really, really, really large. 1 divided by something really, really large is 0. If z is very positive, then e to the something negative positive is e to the -1,000,000 as well as 0, right? Then you have 1 over 1 is 1. Okay, so the function is here and is here, and what is it right in the middle? It's 0. What is it here? What is it here? Someone said it. It's basically 1/2, right? So it kind of looks like this, right? Okay, so the nice thing is, this makes a lot of sense, right? So it means that if I'm really, intuitively, right, I have my hyperplane W, and I have a positive point here, right? As a positive, as label 1. What does W transpose X measure? W transpose X essentially measures how far away are you from the hyperplane, right? So it says if you're, here are my positive points, here are my negative points. If you're really far away from the hyperplane on the positive side, right, then basically I give you a probability of 1, right? And if you're really, on the wrong side, then I give you a probability of -1, okay? Sorry, I moved the... Sorry, actually, I made a mistake with the y here. This should actually, there should be no y here. You're not always multiplying with.
The y goes in front. You forgot that we
Sorry, this equals positive. Yeah, that's right. Sorry. Well, you got it still right. Typically, you actually have a plus b here, which you can absorb as an additional dimension, just like the perceptron. Okay, so basically, you can either basically say there is a plus b, or there's not. So, any questions? So, one more time, if you take a Gaussian naive base and you fit it, what you get is the following expression here. And you basically get some formula for W and some formula B, just the same way that we just did it for the multinomial distribution. Okay? So you take your data, you estimate all these little Gaussians, and then basically, this gives you a vector for W and gives you a B. And then what you do is for every single data point, you just stick this into this equation, and it gives you some value between 0 and 1. And it turns out that's exactly the probability that the class is positive. Okay? All right. So this is great. But we can do something even better. And here's what it is. So basically, what we're doing here is, right, we get this, we're modeling P of X given Y, right? We're modeling the data given the label, and then we get our W and our B, and we get this formula. And that separates the two distributions from each other. And as we've seen earlier, that can be problematic, right? One of the distributions are not actually exactly Gaussian, right? Then you're not separating the data, you're just separating these two Gaussians, which actually do not really correspond to your data. So here comes the brilliant idea number 1. Why don't we, if we're really interested in P of Y given X, right? And we know that the Gaussian naive base at the end gives us exactly this expression, right? Can't we just set W and B, instead of estimating the parameters of the distribution, can't we just estimate W and B directly? So, right, we basically have our data, and we estimate this distribution to get these, get these two distributions here. We estimate the distribution of the positive points and negative points. That gives us a W and a B to separate these two distributions. Well, wait a second, right? We have a closed form here. We have this beautiful formula. Can't we just, instead of estimating the parameters of the distribution, can't we just estimate W and B directly? And that's exactly what the discriminative approach is. So that's what logistic regression is. And this is an algorithm that's really old. Statisticians have known it for a long time. And it's the discriminative counterpart of naive Bayes, right? So the naive Bayes, you estimate P of X given Y. And in logistic regression, you estimate P of Y given X. And you also estimate P of Y. So these are parameters theta, and this here has this, I guess some theta prime. And this here has some parameter W and B, right? And so naive Bayes, basically, you estimate these two, and then you get this, right? but in logistic regression, you're estimating this directly. And well, how do we do this? Right? We want to know the best parameters of WB for this distribution. So now, in some sense, what we're doing, we're saying, okay, well, let's just start with what naive Bayes gives us. Naive Bayes gives us this formula at the end. Right? P of y given x equals the following expression. That's now our assumption. Our assumption is that the probability of the label given x has this form. And now we fit it. Right? That's exactly the same thing as what we did with naive Bayes. We made an assumption about the model, and then we fit it. In this case, we just make an assumption about the probability y given x, and not x given y. That's the big difference. Right? So last lecture, I gave you several examples of how to estimate p of x given y, and what is multinomial, Gaussian, and categorical. And in this case, we just flip it around. We say we just estimate p of y given x as parameter w and b. Any questions? Raise your hand if that makes sense. Okay, awesome. So let's do this, right? Geez, I never figured this out. Okay, so what we want to do is we want to maximum, let me just do MLE. So we want to find the parameters W and B that best explain our data. So here's what we do. We say P of y given x, and now we actually have our W here. So this here is our data. This is, you can just say, let me just do this. x1, xn, and we have W. This here is our data. I see. Oh, you know what? Actually, this is a horrible notation. Let me just. Let me just do it the following way. So basically, what we do is we want to maximize the probability of. You can ignore the first one. The vector notation I don't think is particularly necessary. So here's what we do. We go over all our data points from 1 to n. And we say, what's the probability that I get this particular label, right? Given that I have my W and my X, and my W. And if you want to be really, really particular or correct, then you have to make a semicolon here because we're frequentists. So this here is this model here has parameters W and B. So one more time, I go over I assume I have this model P of y given x that has the parameters W and B. And now what I do is I go over my entire data set and say for every single training point, right, what's the probability that I draw exactly the label that I observed, given that I had that vector x, right? So I go through all my emails and say this here is this particular email, turns out it was spam. What's the probability that actually is spam under my modeling assumption? And I would like to find my W and B to maximize this, right? So basically I want to do argmax W comma B to maximize this. I would like to find the W and B that best explain the labels of my data. Any questions? All right, so here's what we do. Oh, we have a product of many, many probabilities. What do? Take the log. Right, good. If you learn one thing in this class, take the log. All right. So we take the log of this whole thing. That's the same thing as argmax W comma B, sum over I equals 1 to n log, P of W comma B, yi given x comma W. And well, we know exactly what this is, right? Because we made that modeling assumption, so we can just plug that in. So that equals sum I equals 1 to n log of 1 over 1 plus e to the minus w transpose x plus b. And there's an argmax here. Yeah. Okay, so all I did is I just took this p, this is the probability of my label given the email or something, and I just plug in the definition, right? So this is our modeling assumption. We say our label behaves the following way. Raise your hand if you're still with me. All right, good, thank you. I know this is tiresome, but it gives me a lot of feedback. All right, and oh yeah, also, sorry, one thing I forgot. You actually have to have this particular label y, so you multiply with y here. Actually, let's get rid of b. Okay, so we can always get rid of b because it's just the same as perceptron. You can just absorb it in your data, right? Okay, we are almost there. If we now take the log of this expression on the right, it's log 1 over something, well, that becomes, the sum I equals 1 to n. Then we have the log of 1. Well, log of 1, does anyone know what that is? Well, I'll leave it as a mystery for now. Log of 1 plus e to the minus y w transpose x. Okay, so log of 1, I will let you know, it's 0. So what that means is we can just take the sum and move it in here. And now we have this expression. And we are stuck. Right? We have no idea how to find the best w that maximizes this equation. Right, so before in the naive base, whenever we did this at the end, we just got some beautiful little formula. It turns out it's just like, oh, it's the ratio of some counts. Well, in this case, actually, it's w is w that maximizes this function. Okay. So, any ideas? Yeah?
Get the gradient and set it to 0.
Get the gradient and set it to 0. That's right. Good, good, good. Get the gradient and set it to 0. Turns out you can try this. I'm not going to do it now because it will fail. So turns out there isn't actually a closed form solution. So it's a very good idea, right? So if you want to minimize, maximize a function, try to find the extreme point. It's a great exercise, but don't get too frustrated when it doesn't work out. If you take the gradient and set it to 0, actually there's no closed form solution for this. So, well, one thing we can do is we can just look at this as a minimization problem. If you remove the minus, so now it's argmin of w. So we can think about what this function looks like, right? And it turns out it's a function that actually is convex. So it's a function that looks something like this, right? And here's my w, and this here is the function that I'm trying to minimize. And turns out when a function is convex, and I'm trying to find the, trying to find the minimum, we can use things called hill climbing methods. So basically what we do in a nutshell, we start with some w, and then we basically estimate which direction goes downhill, and we keep going downhill. Yay. Okay, good. So we will get to this next lecture. Let's try one more thing, right? This was MLE. What if we do map? Right? MLE is not the only thing we have in our tool chest, right? So MLE we are stuck and we have to do something more complicated here, right? So we were really excited, maybe have this better discriminative way of doing naive Bayes, but turns out actually, it's actually not that, it's more complicated. What if we instead of MLE we use map? Does anyone remember what map does? What do we maximize here? So we maximize the probability of P of W given the data, right? So that's the difference, right? So we try to find argmax of W given the data, right? And that is proportional to P of the data given W times P of W. So that was exactly what map was. So this here is exactly the same thing as MLE. P of W is something we have to make up. So we say, well, maybe we can, this is basically a prior belief. So basically, what map does is we're saying, MLE we said, which W and B are most likely, are such that our data becomes most likely. Here we're saying which W is most likely given all the X's and the Y's that we observed. And so we don't know how to do this, but we use base formula, we flip it around, and we say, you know, which W maximize our likelihood? That's the same thing as MLE times this prior over W. And raise your hand if you vaguely remember this. Thanks. So this is the thing that we, the one key difference is now W is a random variable. That's okay. You have to come up with some random distribution, what W is like. And so this is weird, right? This is a hyperplane, right? So what distribution should our hyperplane be from? And so, but typically what people say is, well, it would be good if it's not far from 0. Why is this? Because you can make really, well, basically how far you are from 0 is a measure of how complex the hyperplane is that you learned. That's basically the assumption. So if you have to go really far away from it, if you make something with very large weights, then that basically means you have to learn something more complicated. Something really simple would be something that has very small numbers and is very close to 0. So that's an idea, and we will get to this a little bit in more detail. But you know, a typical thing would be that you actually say, you know, the W is actually normally distributed. So you actually say P of W comes from some normal distribution, right, with 0 mean and some standard deviation. So this here is a vector here. There's also something that will be the homework, so I won't be ruining your fun. But if you actually plug in this distribution and derive the map estimate, what you will get is actually exactly the same formula with a small change here that you actually have plus lambda times W times W for some lambda. So when you do map, you get basically the same thing. It's just one complete additional additive term. And what this does is you minimize this as well. You're minimizing this term here, which says, explain my data. And you're minimizing this term here, which says, give me a simple solution. Right? It doesn't help us being stuck. We're just as stuck as before. Let me give you a little demo so that it's not too dry. Darn. Oh, here we go. All right, good, good, good. Okay, so we only have a little time left. So here's what I'm doing. Let me once again draw some points. And so here's, let's say, I draw some positive points and some negative points. And let's do it maybe this way that, I'm kind of fooling. This is certainly not a Gaussian distribution, right? Because I have these outliers here. And now what I do is I fit a Gaussian naive base. And what you see here is basically it classifies most of these points correctly. It basically estimates this distribution and this distribution as two Gaussians and puts a decision boundary right between them. But these are 2 points, right? These two x's are in the minority here, and they basically didn't get modeled, right? The model doesn't explain them. So because we're not separating the data, we're just separating the model that we've learned. Naive Bayes it doesn't really work here. But one thing we can do now is we can actually say, let's optimize the decision boundary, the way we just did. So let's maximize the likelihood of the decision boundary. And this is what happens. Oh, it's magic, isn't it? Oh, here we go. Bam. And now actually the 2 points, the 2 classes are perfectly separated from each other. Okay? So what we're doing is we shifted from basically going from something that just estimates the distribution to something that actually estimates the likelihood on the data. Any more data sets that people want to see? Maybe time for one more. Who wants to challenge logistic regression? Yeah, overlapping?
Something that's like not linearly.
Okay, good, good, good. Let's see. You guys are mean, of course. Yeah, trying to torture this pure little naive base. So let's do this. We have some positive points, something like this, and now we have some negative points. Where should I draw them? So this is not linearly separable. Is this fair, or do you want to be even meaner? I don't know.
Meaner.
Ah, all right. Okay, here we go. Okay, this, you want even up? Okay, all right, here we go. So let's say what naive basis does. Actually, it's not that bad, actually, because they're approximately Gaussian, right? In this case, logistic regression cannot separate them, but it will adjust the hyperplane. And I guess what it does, basically, there's more points here that actually crosses, so it corrects the hyperplane. You have fewer misclassifications by moving it over here, right? So the likelihood of your data actually is better if you move the hyperplane a little bit to the left. All right, I leave you with this to think about. I see you all on Friday.